Hello, in this video I'm going to go through a couple of starter questions concerning Newton's second law just to get us in the zone, make sure that we're thinking in the right way, get our basic skills in place. So we got a particle of mass 2 kilograms moving on a smooth slope, so no friction, acted on by a force of 4 newtons acting parallel to the slope as shown. So it's just this picture. Slope is inclined an angle alpha at horizontal where tan alpha is 3/4. Work out the acceleration of the particle. Now they like tan alpha is 3/4 because also if you think of your trig, that if we've got alpha there and then we've got opposite over adjacent being our tan alpha 3/4, then the hypotenuse must be 5. So if tan alpha is 3/4, then that means that sine alpha is equal to 3/5 and that cos alpha is equal to 4/5. So you see quite a lot of questions where they'll pick out this tan alpha is 3/4 because it's just useful. You don't have to keep going to the calculator all the time. We can do everything in fractions. So we're going to be, we want to work out an acceleration and they've given us a force. So as soon as you see these two things together, we know we need Newton's second law. So always good practice to write down what it is that we're using. So Newton's second law, we can quote the F equals ma as the formula we're going to use for this. We can use it because the mass is constant. It's just staying here at 2 kilograms. Remember, force is actually the rate of change of the momentum. So that reduces to F equals ma if the mass is constant, which it is in this case. So we can now work out, we know that the acceleration is going to be parallel to the slope. I mean, it's not going to suddenly just jump up in the air or anything like that, because that's not how life works. So we just need to resolve parallel to the slope. And let's mark on our other forces. So we've got weight coming downwards, so that's going to be 2g because it's a 2 kilogram mass, and then we've got our normal reaction force, which we just call r, but that isn't going to affect anything because it's not acting parallel to the plane. So when we resolve parallel to the slope, then our resultant force, let's mark on our acceleration, let's assume it's going upwards, which is, may or may not be the case. We don't actually know, but I'm going to put it as that's our positive direction. So we can say going up the plane, we've got 4, and coming down the plane, so we're going to subtract it because it's going in the opposite direction. We're going to have this angle alpha is coming in here. So we want this component going down the plane. So that is going to be 2g sine alpha. And that is going to be equal to our mass, which is 2 times the acceleration. And we know that sine alpha is 3/5. So that helps matters in here. So we've got 4 minus 2 times 3/5, so 6/5 of g. 6g over 5 equals 2a. So it's actually going to be moving down the slope, we can now see. We can divide everything by 2. So we've got that a is equal to 2 minus 3/5 of g. And then whatever we decide g is going to be, we can stick that in. So say we had picked g as 10, they haven't told us what to use here, but if we really rounded g to 10 meters per second squared, then we're going to have the acceleration is minus 4 meters per second squared. So that's down the slope. So yeah, pretty straightforward. And we will be using this so many times. This is just the standard process of applying Newton's second law. Okay, we're going to start adding in more and more complicated stuff and connecting particles together and having friction and all manner of other things going on. But it's still the same method that we're going to be using all the time. So I'll just put in a minus 4. I think that's what I said it was, wasn't it? Meters per second squared. So that was that one. Let's ramp things up a little bit then and change the angle of this this force. This is more or less the same question. We've got a force of 30 newtons, 5 kilogram mass, resting on a smooth slope, inclined at 30 degrees. Find the acceleration of the particle. So we see we're going to be doing exactly the same thing here, really. We've got our weight coming down here, which is our 5g, because it's a 5 kilogram mass. And then we're putting all of the same things again. So we'll have, you know, Newton's second law. And it is worth putting all this stuff in. F equals ma. Then we're going to resolve parallel to the slope. We can put in our acceleration. I'm going to put it going up the slope again. You never know what's going to happen. And then we do all the same sort of stuff. We know we've got to do a few things with angles, because of course that's going to be 30 degrees as well in there. So going up the slope, we're going to have 30 cos 30 degrees. Down the slope, we've got 5g sine 30 degrees. And that is going to be equal to our mass of 5 multiplied by our acceleration. So we can plug all this all in. We know that cos 30 is root 3 over 2. So we've got 15 root 3 minus sine 30 is a half. 5g over 2 is equal to 5a. We can divide everything by the 5. So 3 root 3 minus g over 2 is equal to a. So yeah, that is going to be, I mean, that's going to be 5 coming off of there. Well, it's going to be close. It's not going to be a very big number all in all. I'd have to go, maybe I will type this one into the calculator and see what we get. I'll put in a g is 9.81, I think, for this. So 3 multiplied by the square root of 3. And then what we're doing, we're taking off 9.81 divided by 2, which is giving us 0.29, so 0.3, give or take, 0.3 meters per second squared. So it is moving up the slope. But yeah, same process again. You just got to get slick at resolving your forces into components and just being consistent in what you're laying out. You know, we're doing the same thing over and over again. It gets quite repetitive, but you want to be really slick at it, because when you start adding in the more complicated questions another 2, 3, 4 equations into this, and we're having to solve them all simultaneously, then you want to be having no room for error on the simple stuff.